Hi, I'm Adam Chalmers. I'm a software engineer at zoo.dev, and I work on KCL, which is the kitty CAD language. It's the programming language that powers our CAD suite called Zoo Design Studio. KCL is a programming language for CAD, and in previous episodes, we've talked about how to use the basics of KCL, like how to make a 2D shape and how to extrude that or revolve it or make any kind of 3D shape from that. In today's episode, we're going to look at patterns. Patterns are a key part of CAD workflows. They're a really important tool for any kind of engineer using CAD software. And today we're going to look at how to do patterns in pure KCL. So let's just get started, hey? We're going to use the pattern function on this cylinder to replicate it several times. So there's a couple of different patterns you can use. The simplest is pattern linear 3D, which takes a 3D object and replicates it. You can see here we've made 10 instances of our cylinder. Wow, 10 instances. That's because the instances is set to 10. We can space them out a little bit more. Let's make the distance, I don't know, 5 maybe? Maybe 10? And then we can change the axis. This is the line on which the replications are occurring. So right now it's set to 333. We can change it to be, straight line along the x-axis, like 100. Or we can change it to combination again. We can make it, 1, 0, 2 to reproduce them, going upwards in space. You can put in any axis here. Yeah, that's the pattern linear 3D. You can also arrange them, instead of arranging them in a line, you could arrange them in a circle. We can use a very similar function called pattern circular 3D. So again, it's making 10 instances. Now, this time we're going to use a little bit different. We're going to make the axis. Let's take 0, 0, 1, 0 is the axis. And for the center of the circle, let's put the center at 0, 0, 0. Now, because the center of the pattern is 0, and I'm also making the cylinder as 0, 0, that's not going to work very well. We're just going to make replicas that are all in that center. So let's change this. Let's put this at, I don't know, 20 on the x-axis, 0 on the y-axis. Let's change the arc degrees to be 360. There we go. That's more like what I was looking for. So here we've arranged them in 360-degree arc, or a full circle, around the center point of 0, 0, 0. And because this started at the point of 20, we're kind of drawing a circle with radius 20 around that center point of 0, 0, 0. We can change the arc degrees, and we can make these, let's do half circle, do 180. Well, then our 10 instances are arranged around 180. Let's make it a bit smaller. Let's do only 5 instances, say. And that nice 180-degree curve we've got is here. Now let's change this a little bit. I'm instead going to replicate a square, or a cube, I mean. We'll make polygon, let's read it by 10. I didn't define offset. Let's say the offset is offset, there we go. Now they're spaced out a little bit more. So let's increase the number of instances, make, say, 10 of these, all looped around the axis. And if we zoom out a little bit, we can see the heads-on pattern we've made here. So we arrange them at 100, 100, and then we pattern them around this center of 0, 0, 0. Now, see this here, rotate duplicates is false. This means that when we copy the cuboid, we copy it those 9 extra times to make a total of 10 replica. It's not going to change their rotation at all. But if you set this to true, they'll all get rotated a little bit as we reproduce each one. So let's change this to true. And now you can see they're all being rotated so that the pattern kind of looks nice. They're all being rotated as we replicate them. So yeah, then we have 2 kinds of patterns. We have 2 different 3D patterns. We have circular and linear patterns. Let's just go through patterning sketches on faces. In the previous episode, I showed you that you can you can start sketching on the face of a model. So let's see how that interacts with patterns right now. Let's build some kind of base. We're going to just extrude a little cylinder out like this. We've got a circle with radius 50, and we're extruding it to a length of 10. And now let's add some little bumps onto it. This box here we go. We've extruded one little cylinder onto the face because we're doing a sketch on this base here. This is the variable base. We're going to use the end face, which is the face that was created when you extrude upwards. That whole new face you created from the extrusion is called end. We're going to do a little circle inside it. And then we're going to reproduce this circle as well using a pattern. I'm going to add a pattern, circular 3D, with 6 instances around the center of 0, doing a full circle. The rotate duplicates doesn't really matter. We can set true or false because they're symmetric. And there we have it. You can use patterns to replicate features on faces. So obviously something like this is going to be really helpful for doing, like a car wheel or many mechanical parts that kind of have radial symmetry around the center. We're going to look at something called a transform pattern. A transform pattern lets you choose whatever kind of direction you want and whatever kind of transformation you want on all the replica on your patterns. So we saw circular patterns, which replicate them around a circle, linear patterns, which replicate them in a line. Pattern transforms are much more flexible. You can do whatever you want to the replica. You can arrange them in space, you can shrink them, you can grow them, you can rotate them. So let's take a look at how we use them. We're going to take this pattern, we're going to change it into a pattern transform. So first we're going to define what happens to transform. We're going to write a transform function. We're going to go function keyword to declare function my transform. It's going to take a single argument called I. And this little @ sign here, this means that I is the special unlabeled argument. Remember I've said in KCL that the first argument is allowed to be unlabeled? When you declare your own functions, if you want that first argument to be unlabeled, you just prefix it with the @ sign. So I is going to be the number of replica you're currently transforming. And the transformation we're going to do is we're going to translate them across the x-axis. So let's just say return translate equals 10 times I, 0, 0, or let's do 100 times I. And then we're going to replace this pattern circular here with a transform pattern. We're going to do pattern transform. We're going to take in the previous pattern, the previous object as a thing to pattern, and we're going to tell how many instances, let's say 5 instances, and the specific transform we're going to use is going to be this my transform function. And there you can see we are repeating it 5 times in space. Now, if you only want to pattern, if you're doing this in a sketch on face pattern, and you only want to do the part you're sketching on face, there's an optional argument. So when it's true, you're going to be only patterning the thing you've sketched on the face. If it's false, you'll pattern the entire thing, including the face in which you were sketching upon. So in this case, I'm happy to use the entire thing. So we've said we're going to pattern it applying this translation. So the first time it gets called, the original kind of represents I equals 0. That's this whole thing here. So the first time it gets called, it'll be called with I equals 1. It'll do this transformation. It'll translate the original by 100. The second time it's called, over here, it'll be translated with x equals 200, x equals 300, x equals 400. Again, this transform doesn't get called on the original. So you can kind of think of it like I equals 0 there. I would try to write my transformations assuming that I equals 0 is the original. I found that's a very natural way to phrase it. So this is kind of being translated by 0. Again, this doesn't actually get called for I equals 0 because that's your original pattern. That's your original object. So we can do a whole heap of other things in this transformation function too. Instead of just translating it, we can also call angle to be 10 times I, and we give it an axis. And the axis we'll do is going to be 0, 1, 0. Cool. So now you can see they're all moving around slightly. We can make this clearer by making the angle a little bigger. Let's make it rotate 30 degrees instead. Yeah, now you can see this peg is slowly rotating with each copy we've made. And if we want to make it even more dramatic, we can make it 50 or so. There you go. Now you can really clearly see it rotating. we can also scale them as well. It's called make a new scale variable. Let's say sc, short for scale, 0.9 to the power of I. That's what I want. It starts off at 0.9. There we go. Now it's getting smaller and smaller each time. So you can see that we're scaling it every time, so it gets smaller and smaller and smaller along each axis. Now we can make it smaller only on the x and y axes, and we can keep its depth the same. There we go. So now the rotation is working nicely. Okay, cool. So let's move on. Let's make a more advanced pattern transform, because right now all we've really done is show like an evolution on the linear transform. But you can use pattern transforms to do some really interesting things. For example, we can use them to make like a 2D grid shape. So let's try that out. We're gonna just define a couple of basic things first. Firstly, let's just make one square for now. Let's find width. Let's say our width is going to be, I don't know, 10. Width equals 10. Here, we've made a square. And let me just align that so it's heads on with the camera. Let me just put a rotate tool. There we go. Now I want to align replicate these in a kind of chessboard style. So let's do that. Firstly, we're going to make a transform function called grid. And our grid is going to look something like this. We're going to have a grid function. We're going to take the number item this is, and we're going to return a transformation on it. So let's firstly figure out which column and row this is going to correspond to. Column is going to be the remainder when you take I and you divide by n. N is going to be the number of columns we have. Let's say 5 columns. I guess just what you estimate. And then the row number, that's just going to be I divided by n, and it should be rounded down to a real integer, to an integer number. And then we can translate them. We can translate an x according to the column and an y according to the row, or vice versa, I think. So let's do a translate. Where a column, we'll have to leave a little gap. Let's say the gap is going to be 2 pixels or 2 millimeters wide. Okay, and now we can finally do our transform. We can do pattern transform. Let's do n times n, because it's going to be a square, and n is the number of columns. And the transform function we're going to use is this grid function here. And yeah, there we go. So we should have 64 instances. Have I overcounted something? I think we have made the gap too small. Let's make the gap bigger. Let's make it 1.5. I guess the gap should be proportional to the width. There we go. That's more like it. So we now have a 5 by 5 grid that you can see very clearly here. This is the row, basically. For the first 5 numbers, 0, 1, 2, 3, 4, when you divide them by 5, it's going to be 0. And we round down with this floor call. So for 0, 1, 2, 3, and 4, when you divide them by 5, they round down to 0. For 5, 6, 7, 8, 9, when you divide them by 5, they round down to 1. That's why their row is being set to 1. I guess I've got this all rotated around, but it's fine. For 10, 11, 12, 13, and 14, when you divide them by 5, they round down to 2, etc., etc. For columns, it's the opposite. With the remainder, when you divide 0 by 5 is 0. And that's this column here, column 0. The remainder, when you divide 1, or 6, or 11, or 16 by 5, it's going to be 1. So shape number 1, 6, 11, 16, and 21 will all be in column 1, and so on and so forth. So it's a nice little trick to be able to use. You can basically just copy and paste this example code. It's in the docs for pattern transform. You can copy and paste this to make 2D grids. It's just like a standard trick you can use. And there's one more property of pattern transforms, which is you can actually skip something altogether. So I think it's called replicate, the property? Yeah. So we can choose whether to skip a certain one. Let's say we replicate every second one only. So let's do if I divide by 2. The remainder after you divide by 2 is 0. Then we'll skip it. So basically, this is checking, is the number even, right? Because the remainder after you divide by 2, well, I guess we could just call this is even. Check if I is even. Because if I is even, then when you divide it by 2, it doesn't have any remainder. That's the definition of being even. If I is odd, then when you divide it by 2, it'll have a remainder. So, oops, let's rename this is even. Cool. So that's a pretty cool and pretty advanced pattern transform, I think. So you can see that pattern transforms are really flexible and useful. You can use them for a lot of different purposes. Really, any mathematical formula you think of, you can put it into a pattern transform. It's just any function of I, really, of the number of replication you're doing. So we've seen you can do linear patterns, you can do circular patterns, and you can do any kind of advanced pattern if you can phrase it in terms of the pattern transform. And the pattern transform lets you not only position them in space, but also choose their rotation. You can resize them. You can even skip showing them. This isn't really useful, but this is just some kind of fun, pretty code that I put together, and I was just kind of having a lot of fun with it. Here's a little example from earlier. Here's my cube tower. This is my little tower of cubes that you can build. So you can see here that what's happening is I'm taking one cube at the start and I'm replicating it a whole heap of times. So here's my function to draw a cube, and I'm calling the cube function once down here with a certain length and a certain center. And then I'm passing it through this pattern transform 25 times. And then the transform function itself is taking each cube and it's translating it down along the z-axis. So it's moving it down proportional to which number replication is happening, I. I'm going to make it wider and longer and flatter each time. So it gets bigger along the main 2 dimensions, and as we go further down, it also gets flatter. And we're also going to turn it by 15 degrees each time. So yeah, it's not really a useful mechanical object, but I think it kind of neatly demonstrates you can do some really cool things with pattern transforms. Wow, it's kind of cool. Useless, but cool. But yeah, I hope these demos of how to use patterns have made it clear how to replicate your geometry really easily. There's one more kind of pattern that we can talk about, and that's a 2D pattern, but I think we're going to save that for the next video. So check that out next time to learn how to use 2D patterns to replicate sketches. And we can do some really cool things like making procedurally or parametric gears with a variable number of spokes and things like that. So see you in the next video. Thanks for watching.